Hello and welcome back. Let's continue with our lecture on general theory of relativity. Now let's get back to some of the aspects of tensor analysis and Riemann geometry. First of the concept which we are going to see today is the concept of parallel transport, which we do without much giving a thought in the case of flat space-time or Rn while differentiating a vector field. This all leads to more natural way of defining the differential operator in the curvilinear coordinate system or in the case of curved geometry. So let's continue with the parallel transport. This is a part of course PH4205 with IISER calc. Let's go ahead. Earlier we have used the spatial notation, that is we use indices ijk. Here they stand for spatial coordinate. Now we use Greek indices, which stands for space-time indices. That's the only difference. Otherwise, this will all go through the same notation. The metric now will have signature, unlike earlier case where we had Euclidean distance. Now we have a pseudo-Euclidean distance. In general, metric will have a time component positive and a spatial component negative. And also, we will not be restricting to specific type of transformation. We will allow all the transformation, inertial or non-inertial. So we will not specify any specific cases. So we denote the transformation from one coordinate system to another coordinate system. We have a one coordinate system which is labeled as a x prime and the another is simply x. We have a bijective mapping between these two coordinate system which we call as a transformation rule, and we know that the functions transform without any difficulties, or they are called the rank 0 tensor. Earlier we have seen the gradient of a function transform like a covariant tensor. It's a rank 1 tensor. Now we are interested, take an arbitrary covariant tensor T mu. It is not this notation, I should have called it some other name, but let's say that we have covariant tensor T mu of rank 1 and we are differentiating or partial differentiating it to produce a quantity A mu nu, or else we can look at mixed indices. That is, we take a contravariant tensor T mu and then differentiate with respect to x mu to produce a mixed rank tensor, one covariant and contravariant indices. Now the question is whether it transforms like a tensor or not. Of course, we know that under inertial coordinate transformation, this would transform like a tensor. This would be easy to show that under inertial transformation, these partial differential transform like a tensor. However, it need to be checked what happens if the transformation is general. In short, our goal is to check under arbitrary coordinate transformation what happens to the derivatives of vector or tensor. Differentiation is very important because we know that the laws of physics are represented in terms of a differential equation. It is important to have a differentiation of a tensor transform like a tensor so that we can transform the laws of physics to an arbitrary coordinate system. So this is what we check. Let us look at the quantity of the form A mu nu, which is given by derivative of a covariant tensor T mu with respect to x mu, and see whether it transforms like a tensor. So the test is to do the standard checks. It is like a standard health checkup. If you go with some expectation, you may get exactly opposite. Let us see what do we get in the test. So we start with the tensor in a x prime coordinate system, which is given by t prime rho, which is differentiated with respect to variable x prime. That is, we are looking at the t prime rho by dx prime sigma. Now we do a coordinate transformation. This transformation, first we express whatever inside differentiation in terms of x coordinate system, which we know that the tensor T transform like a covariant vector, and we can use the rule of transformation of covariant vector to express the component T prime rho in terms of T sigma. This is a standard covariant transformation rule, and we have a derivative. Let us do this change of variable using the chain rule. We can change the variable to new variable, that's a standard thing, and then we can expand the square bracket. that will lead to these two terms, and this factor would remain same. Let's rearrange this term so that we have one term here is looks like a pure transformation law for the second rank covariant tensor. That is what we expect. In addition to that, we also have an additional term which I have again used the chain rule to rewrite in terms of the derivative of x prime. Otherwise, we will have a mixed derivative in two different coordinate system. That is not very convenient. So we can transform to bring it to single coordinate system so that all the derivatives of x alpha are with respect to x prime. So this is what we have is the expression for the derivative of the prime row in terms of a coordinate system x. However, it is clearly seen that the first term is the transformation rule is a second rank covariant tensor, and then the second term simply comes out to be second derivative of the coordinate transformation, and which need not be zero in general. Of course, it is zero if coordinate transformation is an inertial transformation. Then we have the derivative of a tensor behaving like a second rank tensor. However, in general, this need not be zero, and then what we have is our differentiation in principle is not for tensor. So here we have a problem that differentiation of a tensor is no longer a tensor, and this is one of the problem as we see that differentiation is very important for expressing the law of physics. Now, there is a homework problem here. Show that the derivative dt rho divided by dx sigma is not a tensor. Of course, there is nothing much you have to do. You just have to rewrite this equation and submit. However, I want you to write with your own hand and see that the partial differentiation in a curvilinear geometry is in general not a tensor. Let us go ahead and see what is a problem. This means that differentiation is not a tensor. We want differentiation to be a good quantity so that we can write the laws of physics to be invariant in all coordinate system. All gone ahock because of a term which is second differentiation of coordinate transformation. That means we need to have some corrections done to express the derivative. Let us quickly look at the vector field and how to differentiate them both in the inertial and non-inertial frame such that derivative can be somehow made tensor quantity so that it can be transformed without any additional terms from one coordinate system to another coordinate system. What is vector field? Unlike flat geometry, what we call is a vector space is which is defined at each point, that is at point x is equal to p is a one point which may be associated with the coordinate x alpha, and then we might have various vectors at that point, and all together they form a vector space. Let's take another point q which may be neighboring point infinitesimally separated from the original point p, which also has various vectors around that point which may be constructed either from the tangent of the curves going through that point or normals of various surfaces going through that point, depending on you want to construct a covariant tensor or contravariant tensor. Each point defines a tangent space. However, in the case of Rn, it is very straightforward to transform the vector space from one point to another point. We simply drag them around. That is what we have been doing. That is why we usually do not talk about this point at P and point at Q, vector space at P and vector space at Q. In general, they are all identical in the flat space time. However, in the curvilinear coordinate system or in the curve geometry, the point P and point Q may be completely different property, and the tangent vector from P may be not related so much to a point Q with transformation as we do in the flat space time. In general, there might be a very complicated way of defining the geometry, which is usually called the topology, but we will not worry too much generalization. Our generalization requires some minor changes so that we can incorporate the standard structures such as spheres or some surfaces, things like that, and deal with the intrinsic geometry of those. We have vector field or the tensor field is usually defined at one vector from each point. So you choose one vectors and you form a vector field. Now, because these geometries are completely different, the vector field at P need not be connected with the vector field at Q, however close they may be. Now, such kind of a vague generality doesn't really help us. We will have to restrict some way or other. In the case of Euclidean or Rn geometry, we know that they can be simply mapped, and that mapping which we do from one place to another place is called the dragging or parallel transport. Let us look at how do we do a differentiation of a vector in the flat space time. Let's take a point P is equal to xa, which has a vector field defined as a t row of x alpha, and then you have another point Q, which is also has that same vector field which is defined at Q, that is tp of y or xa plus delta a. When you differentiate, what do? Our standard method is we subtract T alpha Q minus T alpha P and divide by the separation between them, delta beta, and then take the limit delta beta going to 0. That gives us the differentiation. In practice, what we got to do is, since these 2 points are very different in our very elementary vector addition and subtraction rules, what we do actually is to drag this vector from P in a straight line without changing its orientation to the point Q and then subtract. That is essentially what we do when we add or subtract our vector in the Rn. What do? We take the vector at P, then pull it along in the straight line without changing its orientation, take it to the point Q, then subtract the vector at Q from what you brought in from P, and then that difference divide by the displacement between P and Q and limit delta beta to 0, and that is what you get differentiation. We do it involuntary most of the time without too much bothering about all these cases. Pulling the vector along a straight line without changing its direction is what we call is a parallel transport. It is parallel because the original vector is transported from P to Q without changing its magnitude or direction, and that is what leads to parallel to the original vector. Now the question is that how do we do this extracting the two vectors at different point in a curved space-time? That is very easy to do in Rn. We have already seen this description. So question is, how do we do it in the curved space or curved space-time? To develop this method so that we might get rid of this unwanted term which we have in our partial differentiation of a tensor in a curved coordinate system. So let us look at the parallel transport, how we can possibly do it in the curved space-time. Let's say that we have 2 points, P of x alpha and Q of y alpha, or it is x alpha plus delta x alpha. Now we have a vector field defined at both places. We have vector Tp at x is equal to P, and we have a vector TQ at point YA. Now our goal is to take a curve P to Q and then move it along and bring it to the point Q. Now you see that there is no such thing as a straight line. It may not be possible to build a straight line in a curved geometry. We will see that in a little more detail in the real example. How do you do it? You got to usually drag it along the arbitrary curve which may not be straight line. In such case, you see that may acquire some additional term when you transport. So that means you are introducing, even if you think that you are bringing it parallelly, retaining the original direction, because of the path itself is curved, transported vector might acquire an additional term, and that is what we represent it by delta t. It is written tp. It should have been written T row. It is an error. So let's call it okay. So this is exactly what we are worried about. When you drag parallelly, what is the meaning of parallelly transporting? Let's look at the example of our straight line as we done in Rn. We are basically retaining the angle between the tangent to the straight line, that is along the straight line itself, and the vector, the dot product with the tangent vector, and then you are pulling it along. So if we do it for the curve, same way, at each point you draw the tangent to the curve and then retain the angle between the tangent and your vector to be same. But the curve itself is moving, so your tangent vector is also turning around. That would lead to an additional component of the vector which is transported from P to Q, and that is what we call is a delta T row. And that is what we have to see how it behaves. Now let us give an overall general expression for this. The two things important here, how do we describe change delta t rho? Now the first thing is that delta t rho would depend on the displacement. We can assume that our 2 points are so close that delta t depends only linear on delta alpha. So this is one of the assumption which we can do, can reduce the delta alpha much smaller to make that this relation is valid. If point P and Q are separated by a long distance, this may not be valid. We can choose a small enough distance for a smooth curve in order that this change in the vector is actually linear. The second one, it depends on the vector itself. Of course, it should depend. If you take a different vector, the change delta t alpha is also different, and in end, you result in having an expression for a t alpha with the following. Depends linearly on the vector itself. It depends linearly on the displacement, delta p and delta q. It should have been Greek indices. Somehow I seems to have missed it, changing from Latin to Greek, but follow it, it is in the 4 dimension. So in general, what we have is a delta t is given as a linear combination of a quantity, the vector t alpha, and the displacement delta alpha. Now we can call the coefficient of this as a gamma, and that the gamma which we are interested. So gamma can be in general depend on position and so on. However, the final property is that the displacement delta t should follow this. Now we have this 3-legged animal, which we may call as a third rank tensor. It's a separate thing whether it is a tensor or not. We have to see. Our goal is to get rid of the additional term which we have incorporated. So that's a very important role of parallel transport, or taking vector from one place to another place, so that we can do the vector analysis for vectors in a different point in a curved space time. That whole concept of taking from one place to another place is called the parallel transport. Now we can call it a connection coefficient, gammas, because they are connecting the vector from two different points, and that is going to play somewhat important role in our tensor analysis. And let us try to understand it somewhat better with some of the examples. Let me stop here and continue in the next lecture on example and about the covariant derivative.